Imagine an AI system, one that doesn't just react, but can actually think before it acts.
Hmm.
An AI that plans these really complex multi-step tasks, and then, this is crucial, if something goes wrong, it figures it out and course
All
corrects.
in real time in messy, real-world situations.
Yeah, exactly.
Yeah,
That ability to reason and adapt, well, it's one of the biggest, maybe most elusive challenges in AI today.
definitely. It's about pushing AI agents beyond just, simple reflexes, moving towards truly intelligent, deliberative action where the AI understands the goal and the steps needed.
And that's precisely what we're diving into today. Our deep dive is exploring a new framework called ThinkAct, vision language action reasoning via reinforced visual latent planning.
Quite a mouthful.
It is. But our mission for you listening is to unpack how this pretty ingenious dual system approach lets AI connect high-level strategic thinking with precise low-level
Right.
actions.
And the problem ThinkAct tackles is, well, it's a big one in visual language action models, VLA models.
Mm.
These models, they're often great at understanding images and text, answering questions about a picture or writing captions,
Sure, we've seen that.
but they tend to struggle with actual multi-step planning, especially for, say, long-term goals or adapting when things change unexpectedly, like in a dynamic environment.
Why is that, typically?
Well, traditionally, many VLA models map inputs directly to actions. It's sort of an end-to-end thing.
Ah, so they skip the reasoning step.
Essentially, yeah. They bypass explicit, deliberate reasoning and even newer approaches, like using chain of thought prompts, which guide step by step.
Which sound promising.
They do, but they still face challenges. Like, it's expensive to create all the high-quality reasoning data you need for training. And there's always the risk the model just overfits, learns patterns without truly understanding.
Okay, so that's the setup. What's ThinkAct's solution?
ThinkAct comes at it with this dual system framework. The real breakthrough, I think, is how it teaches these multimodal large language models, MLLMs, to generate really sophisticated reasoning plans.
Okay.
It uses a unique system of what they call action-aligned visual rewards.
Yeah.
It's a clever guidance mechanism.
Action-aligned visual rewards.
Right.
Okay, so what can you expect from our discussion today?
We'll break down this dual system setup.
The thinking and the acting part.
Exactly. We'll dig into how ThinkAct actually learns to reason and then highlight some of its standout capabilities. Things like few-shot adaptation, planning over long horizons, and maybe the most surprising bit, self-correction.
AI fixing its own mistakes. Okay, let's get into the architecture.
Yeah.
How does this dual system work?
So at its core, you've got this separation. The thinking part is the reasoning MLLM. They call it
Yeah.
U.
The thinker.
Right. Think of it as the high-level brain. Its main job is generating these embodied reasoning plans.
Embodied reasoning plans. What does that mean in practice?
It means it doesn't control the robot's individual joints, not directly. Instead, it figures out the high-level strategy. So if the task is complex, like make coffee, it breaks it down. First grab the mug, then put it under the machine, finally hit brew. It plans the what and the order.
But not the tiny movements needed for each step.
Exactly. Not the fine-grained how. That comes later.
Got it. And you mentioned the secret sauce is how it learns these plans,
Yeah.
using those visual rewards.
Yes, precisely. It's incentivized through reinforcement learning. It learns to maximize these action-aligned visual rewards.
Why visual rewards? Why is that important?
Because they ground the MLLM's abstract thinking in, well, visual reality, in what the robot can actually see and do. This helps overcome a classic robotics problem, sparse rewards.
Where the AI only gets feedback at the very end.
Right, which makes learning really hard for complex tasks. Instead, ThinkAct gets this continuous, meaningful visual feedback. And there are two key parts to this reward system.
Okay, let's break those down.
First, there's the goal reward, a goal. This basically encourages the model to anticipate success.
How does it do that?
It compares the predicted start and end points of the gripper's path in the plan with the actual goal points for the task. The closer its prediction, the higher the reward. So it learns to aim correctly.
Makes sense. And the second part?
That's the trajectory reward, RTREG. This ensures the planned path isn't just aimed right, but is also, physically plausible, like a sensible movement.
Physically plausible. How does it judge that?
It matches the predicted trajectory against a whole distribution of successful human-demonstrated trajectories. They use a metric called dynamic time warping distance.
Dynamic time warping sounds complex.
It basically lets you compare two movement patterns, even if they happen at slightly different speeds. So it checks if the AI's planned motion looks like a natural, efficient human motion for that task.
So reward for hitting the goal, reward for moving sensibly.
Exactly. And the overall reward signal driving the learning is mostly visual, about 90% combining both goal and trajectory rewards. The other 10% is just for, like, format correctness of the plan.
Okay. And the output of this whole thinking process.
It gets compressed into something called a visual plan latent. They denote it SICK. Think of it as a compact summary of the high-level plan, the intent.
A compact intent, which then guides the acting part.
Precisely. That brings us to the action model, or this is the low-level executor. It's responsible for actually carrying out the actions robustly in the environment.
And this is a separate model.
Yes, often a powerful transformer-based policy. The paper mentions using diffusion policy, which is quite large, 432 million parameters. So it's a sophisticated actor.
And how does it connect to the thinking part, to that visual plan latent?
It's conditioned by it. There's a component called a latent projector, specifically they use a Q former, that acts as the bridge. It translates that high-level latent plan, CT, into instructions the action model can understand and execute.
Okay, so a translator between the thinker and the doer.
Exactly. And what's really clever is the asynchronous design.
Asynchronous, meaning they don't operate at the same speed.
Right. The reasoning MLLM, the thinker, can think slowly. It might generate a new plan only every, say, 75 steps or actions, like on the Learbro benchmark.
Taking its time to strategize.
While the action model, the doer, executes fast control. It predicts and performs actions at every single step, constantly adjusting based on immediate sensor feedback.
Ah, I see. That separation sounds efficient.
It's crucial. It lets the system do high-level deliberation without getting bogged down in constant low-level recalculations. Think of it like a CEO setting strategy versus the team executing day-to-day.
Okay, that makes sense. So you have this thinker and this doer. How are they trained to work together so effectively?
It's a multi-stage process. It's quite layered.
Layered learning, okay.
First, you do an initial cold start for the MLM, the thinker. Maybe using a pre-trained model like Quen 2.5 VL7B. You feed it supervised data visual trajectories from datasets like OpenX embodiment, OXE, or Q&A tasks from RoboVQA.
So giving it some basic grounding in robotics, vision, and language.
Exactly, building that foundation. Then, kind of in parallel, the action model gets pre-trained extensively.
On what?
On huge data sets of robot demonstrations. Again, something like OpenX embodiment, which has tons of diverse robot movements. This gives the action model a really strong general base for executing actions. It learns how to move, grasp, interact.
So pre-train the thinker, pre-train the doer, then what?
Then you refine the MLLM, the thinker, using reinforcement learning. That's where those action-aligned visual rewards we talked about really come into play.
Ah, so this is where it learns to generate good plans based on the visual feedback.
Precisely. It optimizes this high-level reasoning using that reward signal. And finally, the action model gets its own final training phase.
How does that work?
It learns to adapt to new environments and tasks by taking the plans from the now-frozen, well-trained MLLM thinker and using those plans to condition its actions.
So the thinker is set, and the doer learns to follow its plans effectively.
That's the idea. This layered approach lets each part specialize and then integrate smoothly.
Okay, so it sounds sophisticated. How does it actually perform? What do the benchmarks show?
The results are pretty compelling, especially in robot manipulation tasks, on standard benchmarks like SimpleRenv and Libro.
Which are known for being quite challenging, right?
They are. They cover a range of complex tasks. On SimpleRenv, particularly in tasks needing precise visual matching, ThinkAct significantly beat its own baseline action model, DT policy. It hit success rates up to 71.5%.
That sounds like a solid improvement. What about Libero?
On Libero, which is maybe even more diverse, it achieved the best overall success rate reported at the time, 84.4%. That surpassed other leading VLA models like OpenVLA and CoTVLA.
So it's holding its own against the state-of-the-art in manipulation.
Yes, it demonstrates robust performance across many different robotic tasks.
Yeah.
But it's not just manipulation. It also excels in embodied reasoning.
Planning and acting intelligently in more complex scenarios.
Right. It did really well on benchmarks like EaglePlan Dench 2 that measures multi-step planning in daily life situations. And RoboVQA, which tests long-horizon reasoning in robotics through question answering about actions.
And the scores there?
It got 50.1% accuracy on EaglePlan Bench 2 and a 69.1 BLEU1 score on RoboVQA. That BLEU score, basically, it measures how well the AI's generated reasoning steps match human examples word by word.
So it's not just doing the task, it's explaining its reasoning coherently.
Exactly. It shows a strong grasp of the planning process itself, linguistically.
Now, you mentioned something earlier that sounded really interesting, few-shot adaptation, learning from very little data.
Yes, this is one of the standout capabilities, I think. ThinkAct shows a remarkable ability to boost the action model's adaptation to new tasks or environments with very few examples.
How few?
On that tough liberal benchmark, it significantly outperformed other methods, even when given just 10, or sometimes even only 5, demonstrations for a brand new task.
Only 5 examples. That's impressive.
It really is. It highlights how having that explicit reasoning component dramatically enhances the system's ability to generalize and adapt quickly. You don't need massive data sets for every new skill.
That has huge practical implications.
Okay, but maybe the most mind-bending part you hinted at was self-correction. Can it really spot its own mistakes and fix them?
It appears so. The research shows these emergent self-correction behaviors, which are quite fascinating.
Emergent, meaning not explicitly programmed, but arises from the system.
Exactly. They provide some compelling examples, like, say the robot is trying to move a cream cheese box and accidentally drops it.
Okay, a common failure.
The reasoning MLLM, by watching short video clips of what's happening, can identify the failure. It might internally represent something like, the box has fallen.
It recognizes the error from the video feed.
Yes. And then it generates a revised plan. Like, okay, new plan, regrasp the dropped box, then continue with the original goal.
Wow, so it replans on the fly based on the error. It does. Another example. If the robot's struggling to grasp a mug, maybe the angle is wrong, ThinkAct can detect that struggle and then replan the gripper's position for a better attempt.
How does it detect the struggle? Just visually?
Primarily visually, yes. By observing the execution over short segments, the MLLM can infer that the action isn't succeeding as planned and then trigger that replanning process.
Oh.
It reflects and corrects.
That feels like a step towards more genuinely robust AI. And did they test how important those specific reward components were? The goal and trajectory rewards?
They did. Through ablation studies, they systematically removed parts of the system to see the impact.
And
And it confirmed that both the goal reward and the trajectory reward are absolutely crucial. Removing either one significantly hurt performance.
so you really need both, aiming correctly and moving plausibly.
Yes. The study showed that this action-aligned visual feedback, integrated through reinforcement learning, is critical for effective multi-step planning. In fact, when they removed both visual reward components, the performance was barely better than just basic supervised training.
So that whole reinforced visual latent planning idea is really the core innovation driving the performance.
It seems to be, yes. The careful balance and the synergy between those two visual feedback types really enable its capabilities.
So wrapping this up, what's the big picture here? What does ThinkAct mean for, the future of AI?
Well, I think it represents a really significant step towards AI systems that are more deliberative, more thoughtful, and more adaptable in the real world. Embodied AI.
Moving beyond just reacting.
Exactly. By reinforcing this ability for visual latent planning, it truly enables AI agents to, as we said at the start, think before acting.
Which leads to more robust actions and that amazing self-correction capability.
Right. It tackles these long-horizon tasks better. It unlocks things like few-shot adaptation, which is hugely valuable. It's really about bridging that gap.
The gap between abstract, high-level planning and precise, low-level control.
Yes. And doing that effectively, as ThinkAct seems to do, could really change how we think about intelligent action in AI, moving beyond just getting tasks done to, well, truly sophisticated problem-solving in complex environments.
It certainly paints a picture of AI that's less brittle, more capable in the messy, real world.
It's a fascinating direction.
Yeah.
A glimpse into a future where AI might interact with the world in a genuinely more thoughtful way.